Hello and welcome again to my Physical Science online video lecture supplement series. Today's video is going to be another post-quiz review, and in this particular video we're reviewing the results after the temperature and heat quiz from my lecture class. So let's go ahead and pull up the item analysis to see how we did. This was the fifth quiz of the semester, so we're kind of just past the mid-semester mark, and actually that means that we're entering week number 6. So as a helpful little reminder, please schedule some time to take the midterm in the class. With that said, it doesn't look like this quiz went very well for us. It looks like you guys kind of broke the even odd curse that you've been through, but unfortunately you broke it in the wrong direction. This was an odd numbered quiz and you did not very well. That's a bummer. Let's see though what actually happened on this quiz. So it looks like there's a few questions that were pretty difficult for the class as a whole. This one says there were 7 hard questions as measured by the fraction of points that people got. Of course, this says it's difficult if there's fewer than 30% of the points obtained. And I noticed in looking through this quiz that quite a few people had none given as a common answer on the quiz. That basically means that you didn't submit an answer, or to me that says maybe you gave up on the problem without finishing it. Maybe you had no idea how to approach it. I'm not going to go through all of these problems in one fell swoop. In fact, I'm going to mostly concentrate on these 2 problems here that that all 19 of you attempted, but that very few of you actually got correct. I will say that I notice the average time is still well under the 90 minutes that I've been giving everybody. So that does say that you all, or on average, that you have plenty of time to go back and double check your work. That would be my first piece of advice to everybody in general. Let's look though at a couple of the more difficult questions on here. And I should add as a aside, some of these other questions that were pretty difficult, I sent comments along to you in your advice to student or advice to learner. There's a sort of a feedback to learner category when I'm grading the quiz, or regrading the quiz I should say. So you might want to read through that, because I did send back some additional comments on some of these questions. With that said, let's go ahead and look at these 2. The problem which gave people the most difficulty on this quiz was the one that was labeled Emmy X59. That basically means that it's a modified example from the notes, and specifically that it was example 9 from the notes on lecture set 5 on chapter 5. And actually, historically, this one has been one of the harder questions on the quiz, and it's been hard enough that I have made a specific example for it, hence it's a modified example, and in fact have an entire separate video in which I go through that example. So let's go ahead and work through this problem in this video as well, since a lot of you had so much difficulty with it. Basically what we have is that we have added an amount of heat to some water. So this is the heat, this right here is the mass, and this right here is the initial temperature. I'm going to label that as Ti. So we have heat equals 1.00 times 10 to the 7 joules, and that's the total amount of heat that's being added. So what is it that this heat can be used to do? There's several things. One is that it can raise the temperature of the ice. So I'm going to abbreviate that as raise the temp of ice. The next thing that it can do is melt the ice. After that, it can raise the temperature of water. So then once it raises the temperature of water, it could vaporize or boil the water. And then it could raise the temperature of the steam. So vaporize water, and then finally raise temp of steam. So let's look at each of these in turn, because what we're going to do is we're going to treat this as a sort of heat budget. By the way, this right here, in a sense, we're doing physics, but you can apply this particular problem in some ways to concepts outside of physics. For example, maybe you are financially responsible and you try to keep a budget each month. You could think of this as an analogy then. This right here is sort of like your income. So this is the income, and it basically is the thing that decides the budget. So you could think of this as being analogous to like a take-home salary. So when you design a budget for the month, assuming you're on a monthly cycle of salary and of bills and everything, usually the way that you would approach it is you'd say, okay, I brought home so much money for this month, and that money needs to be used to pay for my mortgage or my rent. It needs to be used to pay for all of my bills, like the electric bill and the water bill and the phone bill, cable if you have cable, and so on. It needs to be used to pay for my groceries. It needs to be used to pay for my ability to eat out, buy clothing, buy furniture, take care of the kids, and so on and so forth. So this right here is sort of your income in this analogy. These things right here are sort of like your expenses. So the slight change to the analogy is that these have to be paid in order. And I suppose that there is a certain sense in which that's true of your monthly budget as well. You have to pay for, let's say, your rent, or if you have loans that you're paying off, you pay those, or your food bills, that kind of thing, before you pay for things like entertainment or the ability to eat out. So in a sense, we have to pay for this thing first, then we can pay for this, then we can pay for this, then we can pay for this, and if there's any money left over at the end, or if there's any heat left over at the very end, we are allowed to pay for this. So let's see how much each one of these things costs. And again, there's a sort of fixed amount that each of these things is going to cost that's determined on how much mass there is and how much you're going to be changing the temperature. So the cost of this thing is that the heat to raise the temperature of ice, I'm going to call that Ti for temperature change in ice, is the mass of the ice times the specific heat capacity of the ice times the amount that you're going to raise the temperature by. So there is a hint up here that says that it melts, so this means that we actually are going to raise the temperature up to the melting point. The melting point is at 273 Kelvin. So this right here, what we may have to look up, by the way, is what is the specific heat capacity for ice. You can pull that out of your book or out of your note. So let's pull it out of our notes this time. Here, by the way, is that example that I work in the other video and that's in your notes. We need to kind of scroll up a little bit to try and find where is the specific heat capacity for ice. And in fact, you can see here that we're going through latent heat of various materials. In fact, I'm going to go ahead and, because I've got this table open, write those two down. This is in kilocalories per kilogram for both of these, and so you see that this is 80 for fusion, 540 for vaporization. Let's go ahead and write those down. So the latent heat of fusion goes with melting, and so I'm going to write that here. Latent heat of vaporization would go here, and that was 540 kilocalories per kilogram. So we've written those two down in case we need them later. Now let's go back and look up, though. We're looking up for the specific heat capacities. Alright, and the specific heat capacities we actually find back in table 5.1. And the things we might need are for ice, and you could see it in kilocalories per kilogram degree C or in joules per kilogram degree C. Since we're actually looking, since we have been given a heat in joules, we're going to use the one that's in joules per kilogram degree C. So we need 2100 for ice. For liquid water, it's 4,186. And as it turns out, for steam, at 1 atmospheric pressure, which is what we'd be working at, it's also 2100. So we're going to go ahead and write down those three numbers as well in case we need all of them. Certainly we will need it for ice, we may need it for steam, and we're probably going to need it for water. Alright, so here I've written it down. I'm using CPI for ice, CPW for water, CPS for steam. So in this case it's 2100 joules per kilogram degree C. 2100 joules per kilogram degree C. That's the same as joules per kilogram Kelvin, by the way. So this is the same value if we put in kilogram Kelvin. And that's useful because we know that we have to get it up to 273 Kelvin to melt it. So from 263 to 273 means that this right here is 10 Kelvin. So how much heat are we spending? How much of our budget are we going to spend on heating the ice up? Well, we have 15.0 kilograms. We're multiplying that by 2100 joules per kilogram Kelvin, and we're multiplying that by the 10 Kelvin of temperature change that we have. Alright, so let's go ahead and calculate what that is. 15 times 2100 times 10 gives us 315,000 joules. So we can say basically that the heat used for raising the temperature of ice, we're going to call that 3.15 times 10 to the 5th joules. That's the same as 315,000. This right here is a 5, not a 6. Okay, so we're going to need that for later. That's how much we're spending doing this. So what we have left over is this much minus this much, which is still quite a bit. So we're safely able to raise the temperature to melt or begin melting. So now the question is, can we melt all of the ice? So to do that, you use, let's say, heat to melt ice is going to be the latent heat of fusion for ice, which is written over here, times the mass of the ice that we melt into water. So that is 80 kilocalories per kilogram. We're going to probably need to make some unit conversion here. So we can do something like this: 80 kilocalories per kilogram. And that has to be times the 15.0 kilograms, and then we need to do a unit conversion. 1 kilocalorie is equal to 4,186 joules. So 4,186 joules per kilocalorie. So maybe actually write it like this. Alright, so this way we can cancel out the kilocalories and be left over with joules. So now we need to multiply these numbers together to get the heat to melt the ice. So we have 80 times 15 times 4,186, and we end up with basically 5,023,200. So that we can basically write as heat to melt ice is 5.0232 times 10 to the 6 joules. Okay, so that's actually fairly substantial given that we started with 1 times 10 to the 7 joules. If you put these two together and subtract, you get how much is left over for raising the temperature of water. And just to be safe, let's do that step right now. So I'm going to say heat left over is equal to heat minus the heat from temperature of ice minus the heat that it goes into the mass, into melting the ice. So that is going to be 1 times 10 to the 7, or if we want to put it everything in terms of 10 to the 5, we would have 100 minus 50.232 minus 3.15. And that's all times 10 to the 5 joules. Okay, so what would we get if we did that? So 100 is the same, 100 times 10 to the 5 is the same as 1 times 10 to the 7. So we have 100 minus, and this was times 10 to the 6, so we'd be minus 50.232. Okay, and then we need to subtract another 3.15. So this is what we have left over times 10 to the 5th, 46.618. So question, is that enough to raise the temperature of the water all the way up to the boiling point, which is going to be at 373 Kelvin? And my hunch is that the answer to this is no. So in case it isn't, let's put in that heat. Let's figure out how much heat we would need in order to do that. So heat to raise the temperature of the water is mass times Cp times delta T for the water. And so this is 15 kilograms times the specific heat capacity of water, which was 4,186 joules per kilogram Kelvin, times we have to raise by 100 Kelvin to get it to boiling. So the question is this going to be greater than or less than the leftover heat from these two processes, which was 4.6618 times 10 to the 6th joules. So if this number is bigger than this number, then we're going to not make it to the boiling point, and so our answer will be whatever temperature we end up on. So we got to multiply these numbers together and see what we get. We have 15, we're multiplying by 4,186, and then we're going to multiply that by another 100. And looking at this, there's 3, 1, 2, 3. This number right here is basically 6.27 times 10 to the 6. So that's bigger than this one right here. So that means that we're not able to boil the water. Okay, to make the analogy back to keeping your budget, we spent enough of our heat budget on these two things that we cannot spend enough heat to raise the temperature of the water all the way to 100 degrees. So if I was making a budget and I called this, for example, housing costs, rent plus electricity plus water and sewer and cable, all that stuff. And I call this my basic cost of food and insurance, that kind of thing, loans. Maybe I call this my loans and insurance and sort of things that you have to pay for every month that you they're not necessarily there for a living, but they're sort of your financial obligations. And this right here is the basic cost of living. Beyond that, buying food, buying clothes, etc. I find that I'm going to have to budget to buy cheaper food this month to make it through, and I cannot spend money on entertainment or on, say, junk food or hobbies or what have you. So this is the step that we're going to finally stop on. All right, so coming down here, that basically means that what we can use is this right here is the known quantity. So we have heat left over is mass times specific heat times how much we raise the temperature. And so we can solve for how much we raise the temperature by basically dividing both sides by mass times the specific heat. So M and then specific heat. Delta T therefore equals the heat left over, that was 4.6618 times 10 to the 6 joules. We're going to divide that by 15.0 kilograms and 4186 joules per kilogram Kelvin. All right, so what does that look like when we put it into the calculator? So we actually have 4.6618 times 10 to the 6th, which I have to enter by basically hitting a 6 and a 10 to the x. Okay, so that is this top number, the numerator. Now we're going to divide by 15 kilograms. We're going to divide that again by 4,186 joules per kilogram Kelvin. And what you're left with is 74.2. So this is roughly 74.2 Kelvin. So that's how much we raise the temperature of the water by. Well, T final is basically going to be T initial water plus the change in temperature, delta T. Well, initial temperature was 273 Kelvin because that's when we turned it into water. So the initial water temperature is 273 Kelvin. And to that we are adding 74.2 Kelvin. So if you do that, plus 273, what you end up getting is 347 Kelvin. So this is roughly 347 Kelvin. I usually give a margin of error of plus or minus more than 1%. I think that my margin of error was plus or minus 5 Kelvin. So anything between 342 and 352 should have been correct. And sure enough, if we look down here under the answer formula, it says 347 plus or minus 5. So if you had done this and put 348, it would have counted you as correct. If you did this and put 350, it would have counted you as correct. If you put 344, it would have counted you as correct. It looks like this time around nobody actually got this question correct, however. So that's unfortunate, and I guess my advice on this point would be to go back through this video before your midterm and maybe go also back through the other example that I worked, because you now have 2 examples of this. To be fair, this is probably the hardest question that you have to do at all anywhere in the physical science course with me. So I would strongly advise reviewing this a few times because this one is relatively difficult compared to other physical science questions. Nevertheless, it's good for you to face a few difficult questions through the course. So please do review this video, review the other example that I have already worked with this problem, which had different numbers. And hopefully, if it shows up on your midterm, you'll redeem yourself by getting it correct there. All right, scrolling down, the next most frequently missed, and this one was missed quite a bit, only a little under 11% of you got this one correct, was the key terms and matching problem for this week. And the question was, which of the following uses work to transfer heat to a high temperature reservoir? So let's look at the options that you had. The options were conduction, convection, radiation, entropy, heat engine, motor, or none of the above. Okay, once again, this was a key terms and matching question. Now, you probably have noticed at this point in the semester that I can't just give you the key terms and matching as normal on your Blackboard quizzes. I have to modify the wording very slightly because the actual key terms and matching in your book looks like this. So here are the key terms from this week's chapter. Here are the things you can match them with. Now, hopefully at this point you've noticed that the way that I approach this is that I will basically say which of the following options is a force per unit area, for example. So I've picked the thing that you match to, and then I will give you a list of some of these terms. And the correct answer may or may not be one of the terms I give you. There's usually a none of the above option. So this time around, the question was, which of the following uses work to transfer heat to a high temperature reservoir? And this is a key term matching. KTMS means key term matching. So we're looking for uses work to transfer heat to a high temperature reservoir. So if you look down here in the different options that we have, uses work to transfer heat to a high temperature reservoir is option S. So if you wanted to be sure that you're going to get this right, I hope that what you're doing, in all honesty, is you're doing these homeworks, you go through, you do all this key term matching, and then when you finish, what I'm hoping you're doing is that you're going to the end of the book, the stuff that says in matter, this part that says answers to selected questions, and your hard copy of the book has this too. So if you didn't buy the WebAssign access, that's fine. You still have this if you bought your textbook. You go to the answers to selected questions, and this was chapter 5. So let's look under chapter 5. Oops, I scrolled down a little bit too far. Zoom in a bit so that we can actually see what it says here. And answers to matching questions. This is all of the matching questions. The one we're looking for is S, and it says it matches term 24. All right, so you come back here and you look and you see, oh, term 24 is a heat pump. So the answer to this question is heat pump. So now I look through these different options and I look for, where does it say heat pump? Well, this is not a heat pump, this is not a heat pump, this is not a heat pump. These, by the way, are different. They're basically the different methods for getting heat to transfer from one object to another. This is entropy, this is heat engine, which was a very popular choice, as you can see from the number of people who selected it. Motor. None of these is a heat pump, so the answer should be none of the above. So that's how you should have done this. I assume that you did this during the actual homework since it was an assigned question on the homework, but the process is similar. If you've already done the homework, then you already know that the answer is heat pump. So when you get to this point and you look through this list and you don't see heat pump, then you choose none of the above. So just for fun, what are these other things? Well, quite a few of them actually are already among the heat terms that, among the key terms listed for this chapter. For example, here's convection, here's radiation, and here's conduction. So these three were already terms. You should have already known that those don't go with this one because they match with other things on here. You would have found that if you'd done the homework. Case in point, if you look at these three terms, some of which were popularly selected, conduction should have been matched down here to transfer of heat by molecular collisions. Convection should have been matched here as transfer of heat by mass movement, and radiation should have been matched down here as transfer of heat by electromagnetic waves. By the way, I noticed in reading through people's introductions historically that people occasionally will say stuff like, I'm a fan of science fiction, or I like reading science fiction stories, I like reading about space travel, I like reading about or learning about how we find objects in space. There's an interesting essay, and it was actually a Hugo Award finalist this last year by a guy named Ken Burnside. And it's called The Hot Equations, Thermodynamics and Military Science Fiction. And it's actually a pretty good read. I read it over this last summer in the course of reading through the Hugo Awards packet. It basically discusses, among other things, thermodynamics in the context of science fiction. And he talks a bit about how heat can be transferred in terms of conduction, convection, and radiation, and how this applies to basically space opera type military science fiction. And for the interested reader who wants to read something a little different than the usual science textbook discussion of this, I'd highly recommend that essay. He also talks a bit about transfer orbitals and so on. So there's quite a bit of interesting physics in this text. The main reason why I bring it up is because, though, he does discuss these three methods of transferring heat, and specifically the fact that if you are in an isolated system, the vacuum of space, for example, the main method that you're transferring heat is by radiation. And that is basically by having electromagnetic waves leaving from your hot object. It basically acts like a black body emitter, for example. And so that knocks out some of these options that we had. Entropy is, of course, tied into this whole thermodynamics discussion, but it doesn't have to do with how heat is transferred. It just has to do with the law that says that when heat is transferred, you increase the entropy of the system. A heat engine basically does the opposite of what this thing is talking about. It uses the transfer of heat from a high temperature reservoir to a low temperature reservoir in order to do work. And then a motor we'll actually encounter in Chapter 8 does mechanical work by using electromagnetic energy. Basically converts from electromagnetic energy into work. So that's all that I've got for today's video. I hope that you found this helpful, and thanks for watching.